Good afternoon, I'm Royu. I'm here to present our works on course recommendation, which is called the Cognitive Distillation-enhanced Course Behavior Course Recommendation Model. Basically, there are what is we call course recommendation is we want to recommend some course that meets the learner's real-world learning needs. Like there are lots of platforms like MOOC on the website, and we collect their interaction data of different kind of course and recommend what meets their real needs. And basically nowadays, course recommendation methods can be divided into two categories, which is called the course grant methods and the concept grant methods. Course grant method is focused on the course interactions, and concept grant method is more focused on what the concept is included in the course. And we want to find out that by the course they interact, we can find out that if they are good at those knowledge concepts in the course, and we can recommend some similar courses that have the same knowledge concept that really meets the learner's learning needs. But basically nowadays, concept grant methods ignore the impact of the learner's cognitive states, which can influence learners' current learning competencies and future learning needs. What we call cognitive states, it is as shown in the figure right now, it is about the different kinds of ability of the learners to help them learn more knowledge from the courses. So here comes one of the techniques which we call is cognitive diagnosis. It can precisely assess learners' mastery of specific knowledge concepts by analyzing historical exercise interactions, thereby quantifying the cognitive states features. So what we want to do is combine the two different kinds of works, which is course recommendations and cognitive diagnosis, and combine them to get better course recommendation results. But here comes the challenge. The first of all is about the divergent objectives caused by the two different types of interactions, which can result in the gap in the learner's representation as the figure shows. The second one is about the inconsistent data between the two different types of interactions. Like one student may learn 1 or 2 courses in a week, but he may did a lot of hundreds of exercises in the period of time, which will lead to a very huge data imbalance when we are doing this work. So what we do is want to combine the two different kinds of tasks in a better way. And here comes our models, which we call it the Cognitive Distillation-enhanced Course Behavior Course Recommendation Model, which we call it C3REC. Basically, we collect 3 different kinds of interactions, which the one is the learner exercise answering interaction, the one is learner course learning interaction, and the exercise knowledge inclusion. We get the 3 different kinds of relations and made it into the graph. And the whole model is basically made out of 3 different components. The first one is called the dual granularity cognitive diagnosis components. It can model the learner's cognitive states as both the exercise and knowledge concept granularities. Basically, we designed a special graph encoder which is based on light GCN and get 4 different kinds of learners representations and send it into an item response theory based encoder, which is widely used in the cognitive diagnosis task, and get 3 different kinds of students factor, which is called the studying factor, the discrimination factor, and the distinction factor, and then send it into the decoder to get the final logic about if the student can correctly answering the exercise and what their cognitive states is included in the student's factor. And when we get the factor, we run into this cross-behavior learning preference modeling components. The cross-behavior is called the cross relationship between the learner's course learning interactions and the learner's exercise answering interactions. And we made a cross-behavior graph in it, and we send it into a cross-behavior graph encoder and get 3 different kinds of learners representation, and then send it into a temporal cross-behavior attention encoder. Because as we said it before, the students may learn a course, do several exercises, and learn another course, do another several exercises. So we put it together in a sequence temporally, and then send it into a course recommendation decoder. And to combine the 2 different kinds of tasks, here comes the 3rd component, which we call it the triple stage joint learning cognitive distillation components. It is based on the knowledge distillation, which is widely used to combine several different kinds of models like the teacher model and the student models. we use it to exploit cognitive states feature as a prior knowledge to enhance the recommendation model through the knowledge distillation parts. It is basically divided into 3 stages. We first build the cross-behavior interaction graph, and then send the 2 different kind of students representations from the 2 different kind of components, and send it into adaptive gate knowledge distillation mechanism. And then we use a cross-stack cognitive distillation part to help to use the students' presentation from the cognitive diagnosis components as a prior knowledge to lead the cross recommendation parts, thereby to put more cognitive states of the learners to help us better find out the learners' learning needs. And we are trying to answer 4 kinds of research questions in our experiments parts. The first one is about, we use 2 different kind of data sets, which is called MuQubeX. It's a data set from XueTangX, which is an online learning platform in China, and then EdNet. It is collected from Santa, which focuses on TOEIC test preparation. And as the table shows, the result highlights the efficiency of jointly modeling cognitive states to enhance course recommendation as our models outperforms all benchmark baselines. And we also, in the ablation study parts, we make 3 different kinds of variants, and over removing any components degrades the recommendation performance. And notably, the variants which remove the dual granularity graph and cross-learning behavior graph exhibit significant performance drops, and highlighting the effectiveness of our dual granularity cross-behavior modeling in enhancing the course recommendation results. And we also did some hyperparameter sensitivity experiment, and here is showing it in the figure 5. And then we also make a case study. We randomly sampled 1 student who, as the figure we can see, he did well in the University Physics 1 course and the Theoretical Mechanics course, but he didn't do well in the Mechanics and Dynamics course. And we send the students' information into 2 different kinds of, two different models. The one is ours, and the one is randomly. We select the one baseline as the comparison, and we can see that our models recommends the course that may really is more relevant as for the learners' exercise answering behaviors, as they showed you didn't do well in the mechanics and dynamics courses, so we recommend more relevant courses in the list. And it shows that our model can provide better recommendation results that meet the learner's learning needs by considering his or her performance in exercise to capture cognitive states. So this is what we do, and we want to find out the more influence of different kind of studying factors or studying behaviors in the real-world educational scenario to help us better capture the students' learning needs and provide more courses that may really help them finish their studying and meet their needs in the future. And this is what our research in the future we want to do. Thank you for listening.
Very interesting question. So cognitive states are noisy and hard to measure. And how do you ensure that your model isn't amplifying this noise when you have the behavioral data of the learners, and then you are transferring this also to other tasks? So how do you make sure that this is not amplifying the noise?
And this is a very interesting question. And as the figure we first show in our slide, it do has a very big gap between the 2 tasks and in the learner's presentations. And why we use knowledge distillation to combine the 2 different kinds of tasks is we want to try our best to make sure the 2 tasks can be combined in a smoothly way. I don't know if I need to say this, but yes, it will have some noises maybe, because it is a quite different task. But what we want to do in the future is considering more if basically the educational data sets right now, they have a lot of more information, a lot of more features. Like how many times did the student try one exercise, and if he use hints for the exercise, this information can basically show more about students if they really gets what's the course or what's the exercise knowledge inside. So I think if we can put more this kind of information, more kind of these factors into our models, we can make it more in a more I don't know how to say it properly, but maybe in a more like noiseless way.